communication system, the 5G system, it's what is basically this means. So ultra reliable low latency communications means that the system should be up for most of the time, and then you should be able to access its services within very limited time. And then the third aspect is MMTC, which is short for massive machine type communication. So in enhanced mobile broadband, it's all about mobile phones and then how you communicate with we want to go to the internet. But then massive machine type communications, we are talking about this Internet of Things and sensors. So if you consider some kind of a factory setting, there could be many IoT sensors here and there throughout the factory, and then these sensors may need to send out their data frequently to the network so that the network can decide what to do with these measurements. So these sensors can be temperature sensors, humidity sensors, and whatever. So now we are not talking about just one mobile phone, but we are talking about even thousands or millions of devices. So 5G, we also want to give services for these IoT services. So there is like a very big number of devices in such scenario. So, and this shows some examples for these three types of services. So if you consider this enhanced mobile broadband, which you have in your phone, we talk about how many gigabytes in a second that you can transmit. So you want to have very high like data rate. So that means you want to have gigabytes or megabytes as much as possible in 1 second. And an example for that is when you want to stream some like very high definition video or like a 3D video, it requires so much of a bandwidth, or you need so much of a data rate so that you can see the video continuously. So you need to have this kind of like mobile broadband, like enhanced mobile broadband system. And then the second one is this URLLC. So this an example for this is a self-driving car. So if you consider there is two self-driving cars going along the road, then you need to make decisions like very quickly. And because if not, there could be accidents or the two vehicles can collide. So these ultra reliable low latency applications are such kind of applications where it is like the system need to be up, or the communication between, let's say, the first car and the second car need to be like up all the time, so that it can, if necessary, communicate with the front car about whatever in the road. And at the same time, this communication should happen really fast, because otherwise, if it is let's say too much of a delay, then there would be a pedestrian crossing, or there would be another vehicle coming. So this is where this URLLC is important. And then the other one is like I mentioned, where you have so many millions of devices or sensors. So an example for that is like the smart city concept, where it's similar to a factory where you have different sensors, but you consider that you have different sensors in a small city. So in such kind of a scenario, then there will be massive number of devices that need to communicate sometimes with each other, or also communicate with some network, let's say some processing unit. So all of these millions of devices can offload their data to this central node, and then based on that, the central node can make the decision about, let's say, the temperature, and then use them for separate purposes. So these are the main three services supported by 5G. So in order to have these different services, there are like separate, let's say, key performance indicators or KPIs. So an example is that, so you see here, there's in the diagram something called IMT Advanced, and this is this inner sort of circle, and then IMT 2020, it is the outermost circle. So you see the in IMT 2020, the different values are better than what was in IMT Advanced. So IMT Advanced, you can consider it to be something like 4G, and then moving on from 4G to 5G is where the requirements are coming from in this IMT 2020. So an example for the peak data rate that is sent out by the the cell tower, for example, needs to be at least 20 gigabits per second. So that is one requirement. And then the user experience data rate, that is what you observe in your phone, should be at least 100 megabits per second compared to, let's say, 4G, where it was just 10 megabits per second. And then I won't go into spectrum efficiency, but the mobility. So now you can see nowadays we have these like very high like fast moving vehicles like trains. So then these 5G services should be, giving services to these trains which have at some speed of, let's say, 500 kilometers per hour. So if there's a train moving at like 500 kilometers per hour, that means it travels very fast, obviously. And then if you have two cell towers, and then if you move very fast, quickly you can lose access from this cell tower, but then you need to continue the communications to the other cell tower. So then you need to the 5G services need to also incorporate how we can provide such kind of like fast moving vehicles, how we can provide data. Otherwise during the journey, on your train, you might lose the connection. So that is not something that we want. And then the other one is latency, like I mentioned, the delay. So in the connection should happen. That means as long as when you want to surf the internet, the data should come to you with like latency of 1 millisecond compared to what was in 4G, something like 10 milliseconds. So now you see in 5G we are talking about 10 times less delay. And then the connection density, which is important for this machine type communication. So we want to provide services for at least 10 to the power 6 devices in a square kilometer area. So, and then these are anyway some other parametrics, but these are some of the requirements that was in 5G. And then now we are in 2024, almost 2025, and then now there are discussions and also research and so much of happening now how we want to move from 5G to 6G. So now if I move to these 6G services, so similar to 5G, the 6G has these kinds of like services that they want to offer in 2020-30. So as you see here at the center part, you have this enhanced mobile broadband, massive machine type communication, and URLLC that was proposed by this IMT 2020 framework. But now this part corresponds to 6G scenarios. So you see now enhanced mobile brand in the future we'll be talking about something called immersive communication, and massive machine type communication would be something called massive communication, and URLLC is something called hyper reliable and low latency communication. So these are the three main services that were supposed to happen in 5G. But then in 6G, there are now three more cases, as you see here. The first one being AI and communication. So, artificial intelligence and communication. So how we can combine this artificial intelligence for communications for 6G. So that is one thing. And there is also like many research happening on how to do that. And then the other one is ubiquitous connectivity. So ubiquitous means that you should be able to access the internet or whatever service that you want from anywhere in the world. So for example, there might be some areas where there are no cell towers, so you cannot gain access. So in such a scenario, we still want to provide services or like internet facilities or whatever. Then this is where this new technology that is developed is something called non-terrestrial networks, which is basically satellite communication. So how we can use the satellite communication and then communicate with the cell towers in order to provide communication even for areas where there are no cell towers or where there is no cell coverage. And then the focus of this lecture, which I will talk about, is something called integrated sensing and communication. So this is actually the topic that I did for my PhD, and the following slides that you will see are some of the introduction to integrated sensing and communication and what it means. So hopefully you'll have a better understanding by the end what this means. So you see now in 6G, we are talking about these 6 services now, when compared to the 3 services that we were talking in 5G. So in order to have these services, there is again similar to this 5G, there are some requirements. So these are these KPIs, like I mentioned. So at the bottom, you can see in green what are the previous KPIs. I think I lost the screen. I think someone became host and I lost the
Yeah,
screen.
yes, give us a second.
Sure.
Yes, now you're co-host. Okay.
Okay, I hope it's now visible. Okay, so oops. So yeah, so now you can see in green the same requirements or the KPIs that were in 2020, IMMT 2020. So now you see the latency, which was 1 millisecond. In 6G, the latency should be even less. So it should be now between 0.1 and 1 millisecond. And you see now the mobility. Earlier it was 500 kilometers per hour, but now we are talking about something between 500 to 1000 kilometers per hour. And then the connection density now is between 10 to the power 6 and 10 to the power 8, which was earlier 10 to the power 6. And then the other ones are sort of similar. But then on blue, in blue color, you can see more new capabilities that we should have for 6G services. So basic related to coverage and then sensing related capabilities. So sensing what I will introduce you to next, and then this AI related capabilities, and then sustainability is basically about how you can reduce the energy. So it is good for the environment. That means you want to transmit much data as possible, but with less energy, so that then you will be saving energy. Then you will be contributing to the to lowering this global temperatures and so on. And then yeah, so these are the main capabilities that will be expected in 6G. So yeah, before moving on to the next section, I want to ask if anyone has any questions on this, or should I move forward? Okay, it seems there aren't any questions, so I hope it was all good. Then let's move on to this topic, which is integrated sensing and communications. So okay, yeah. So communications, as you know, it involves transferring information between two or more points, right? And then there are two main components in communications: a transmitter, which is usually in our case something called the base station, which is similar to the cell tower that you see. So here in this figure, you can see it's the cell tower. And then the other ones are obviously the receivers, short for RX, and the transmitter is short for TX. And then the receivers are obviously the mobile users. So you can see like someone can be surfing the internet, and then there can be many users. So this is communications, as you know. But then sensing, what sensing essentially means is similar to the functionality of a radar system. So radar system and sensing systems, they are used simultaneous. They are almost the same terms. So there are three steps in a sensing system or radar system. There is a transmitter, TX, which transmits some signal. And there is a target, which could be a vehicle, which it could be a person, it could be anything. And this transmitter signal, when it hits with this object or the target, it gets reflected back. And then there are receivers to capture this received signal. So, and then based on this transmit and receive signals, the radar system will can measure what was the speed of a vehicle, and then something called the range and the angle. So if I talk about the speed, so suppose that this is an example of a police gun, where a police, when a vehicle is moving, it will use this something called the radar gun, and it will do this, and then what it does is it transmits the signal, and then it's reflected from the vehicle and received back, and then you are able to estimate what about to measure what the speed or the vehicle of the velocity of the vehicle is. And then similarly, you can have speed, and this is, you can also use that the radar system for range and angle process. So range essentially means the distance. So a distance from the transmitter to from the distance to the target or the object. So, and then you can also know which angle it is. Is it 0 degrees, 30 degrees, so and so. So this is an example of a radar system in a ship. So you see at the center is this corresponding ship, and then this radar system, transmit the signal in 360 degrees, and then based on the reflections, it can measure, okay, there is one ship here at, let's say, 60 degrees from the vertical, and then this is the distance to that particular ship, so and so. So with the radar system, you are able to measure mainly these three quantities: the speed and the range or the distance to a specific target, and then the angle of that particular target. So, and then so this is in the past, what the case was that the communication systems and radar systems, they were operating separately. So they were like they were not so much in the same, let's say, the geographical area. But since then, from, let's say, 10 to 15 years ago, and if you compare the number of communication systems that you have, it has considerably increased, because in 2010 of this area this year, most people did not have mobile phones, but then every person, even very young ones, even very old ones, they have more and more mobile phones. So more and more mobile phones mean that the communication system, or the 5G system, or the 6G system, it needs to support give mobile services, mobile data facilities, and then what that means is it increases the number of communication systems or the communication users. And then what happens was that both systems, that means the radar system and the communication systems, have started to now operate in the same area. And when that happens, something called interference happens, which means that radar system interferes on the communication system, and the communication system interferes on the radar system. So I will tell you a bit about what this interference means in the next few slides. But then when this interference happens, the performance or the quality of the communication and as well as radar systems decreases. So we don't want that to happen. So that is why there was this need to integrate, that means combine the sensing and communication systems. So rather than them being two separate systems, this in 6G, we are talking about combining these systems together. So that is what is meant by to integrate sensing and communication systems, so that this interference doesn't happen. And when that interference doesn't happen, then the performance can be very high. For example, if you have an interfering, let's say the radar system interferes on the communication system, then your YouTube video, maybe it takes too much of time for it to load. And then where it is less interference, it like loads very quickly. So that's what I meant by this performance. So similar to the radar system, if the communication system interferes on the radar system, what that means is sometimes, let's say, the actual vehicle speed is 40 meters per second, and then if without interference, if it measures as, like, let's say 39 meters per second, but now because of this interference, it can say, okay, now it is like 20 meters per second. So you see now it's the actual speed was 40, but now the measured speed is 20. So you see there's like very much of an error, so that you don't want to happen. So that's why this interference is like very bad, and then we need to sort of minimize this. And then talking about this interference, so as you know, every communication system or every radar system operates around something called a center frequency. So as you know, in your home, you have the Wi-Fi system, and it operates in two frequency ranges, the one at 2.4 gigahertz and another one at 5 gigahertz. So it is the same for a radar system as well. So you see here the S-band radar system, it operates around this center frequency, and then you see it's sort of S-band radar, it goes from 2.1 gigahertz to something like 4 gigahertz. So that we call the bandwidth of the system. So there's a center frequency, so around, let's say, around 3 gigahertz, and then 3 minus 1 gigahertz to the left and 3 plus 1 gigahertz to the right. And then so you have a sort of a bandwidth in this case, or for the S-band radar, something like 2 gigahertz. So just remember there are these two values, the center frequency and then the bandwidth. So for example, in Wi-Fi in 2.5 gigahertz system, if I remember correctly, the center frequency was 2.4 gigahertz, but the bandwidth is 100 megahertz. This 100 megahertz, this is the what contains your data. So if you have more and more bandwidth, that means you can accommodate more and more users. But then if you have less bandwidth, that means you cannot put more users, and therefore the data rate will decrease. So like I mentioned earlier, so now suppose that there is a Wi-Fi system operating at 2.4 gigahertz, and there is an S-band radar system operating around 3 gigahertz. So now you see for this bandwidth, this part, there is this overlap between the Wi-Fi system and the S-band radar system, and then when they are operating at the same time in the same geographical area, that will cause interference. So the interference in here can happen in frequency. So that is just the interference. So just to introduce you what this interference is in some maybe like a logical example. Suppose that there is a room and there is a person B listening to something being said by a person A. So then in this case, of course, the person hears what A wants to say. But then what if we put more and more, let's say a couple of people in the same room, let's say C and D. Now what B hears is something said from A and then something said from C. So the C is something that B does not want to hear, but she cannot do anything. She will still hear it. So this is this unwanted information that you still hear, and that is called interference. So similarly, if in this scenario, if person B hears something from C, it hears also something from A. So in this case, the A's speech is interfering to D. So this is what is basically, and then of course, when you have just 4 people, this might not be an issue, but assume that you have, let's say, tens of people in the same room talking to each other. So then sometimes you have to like go closer to the person. Okay, what did you say? Because you couldn't hear because of all the other noises. So that's the same with this interference between communications and radar systems. So like I mentioned, if you consider this to be a radar system, so you have like I mentioned, a transmitter and a receiver, and then this radar system transmits some signal. In this case, I denote it as xt, and x is just for the variable and t is just to denote time. So there is a time varying signal. And then you see for radar system, this green curve arrow, so it will transmit and it will get reflected and received at the radar receiver. And then based on that, the radar receiver will estimate let's say, the speed of the vehicle. Similarly, you have a communications transmitter and a communications receiver. So in this case, transmit is some signal XC, short for communications, and then the received signal is YC in this case. So these are the green lines denote the wanted signals. But then, like I mentioned, because of this interference, the transmitted signal from XT can leak onto the communications receiver. So now what the communications receiver hears is what the wanted signal coming from the cell tower or the base station, but also this unwanted signal XT. Similarly, for the radar receiver, it only wants to receive this green signal, the reflection, but then because of the cell tower, it also hears this received signal from the communications transmit. So this is, you can see it interferes both the communication system as well as the radar system. So like I mentioned earlier, this interference can happen in either time or frequency domains. So that means this is what it means by to happen it in time domain, meaning that you are receiving the same signals at the same time. So that for the mobile phone, it might be the this YouTube video signal is coming, at the same time you get the same this unwanted signal. So this like I mentioned here, so this YCT is now a combination of two terms, the wanted XC and then the unwanted XT. So, and then like I mentioned earlier in this slide, this interference can happen also in frequency domain. So that means they could be happening on different time instance, but then it is possible that they happen at the same frequency. So like I mentioned here, the Wi-Fi system's frequency bandwidth overlapping on the S-band radar system's bandwidth, then it is this interference in frequency domain. So this I just show here what it means, the bandwidth of the signal. So bandwidth is this the useful data of the signal. So yeah. So like I mentioned, this interference can happen either in time or in frequency, and when either of that happens, it interferes each system and it reduces the performance of each system. All right, and then because this was what I talked was about the past. So why was there need to this integrate sensing and communications? Because of this interference, it can happen in time or in frequency. And then something called the RF spectrum. So RF spectrum is something like this. So you see, in order for anyone to transmit, you cannot just transmit on any frequency, but you should buy it from some entity, legal entity. So for example, in Sri Lanka, we have Dialog, Mobitel, these different telecommunication service providers. And then what they do is, suppose that they want to transmit some 5G signal in this, let's say 3.5 gigahertz, then they should, apply this bidding procedure from this separate entity, and they must buy the legal right to transmit on that frequency, because you cannot just transmit on any, because otherwise if everyone can transmit whatever they want in different frequencies, then no one will be able to communicate with each other. So because of this reason, there's this global entity that divides, okay, you can use this frequency range in gigahertz 5G, and then you can use this range for Wi-Fi. You can use this for whatever the other communication system. So, and then in order for you to transmit on that, you should pay something for this legal entity and buy the requirement to so then you can buy, so that you can transmit. Of course, there are these free frequency bands where you can transmit. So for example, I think this 2.4 gigahertz in Wi-Fi, it's this kind of like a frequency range, but this 5G ranges, they are like you cannot just, you should buy the right. So if the RF spectrum or the radio frequency spectrum, it's what is this basically spectrum means like the in the frequency going from the 2 gigahertz to 10 gigahertz. So that is the 2 to 10 gigahertz RF spectrum, radio frequency spectrum. So, and this spectrum is scarce, because if suppose that there is this, let's say 5 gigahertz band, and then if a Dialog is transmitting their data on this particular bandwidth, then if Mobitel also tries to transmit on this particular band, what happens is there will be interference between Dialog and Mobitel services, though neither Dialog services nor Mobitel services will be able to happen. So that's why if you have Dialog services, then the other one should be a little bit away from the Dialog bandwidth. The Mobitel one, they should be a little bit away from. So because then you need to buy for this requirement. So that's why. And then once both Dialog and Mobitel have this range, let's say 5 to 5.5 gigahertz, then let's say something like Etisalat, they cannot use this range. So then you see, when someone acquires it, then it reduces the opportunities for the other. And then this RF spectrum is scarce, or it's like, because you cannot, there is not so much, because if you lose 5 to 5.5 gigahertz, you cannot have it back. So because it's some other person's. So that's why it is scarce. So what I meant here in this RF spectrum being scarce. And now what we want to do is, because like I showed you earlier, this frequency or the time domain interference, it will decrease the performance of both. What we mean by this RF convergence, what it means is that the same RF spectrum is jointly used for both communications and sensing. So you use this same bandwidth for communications and sensing, but not just as it is, but in some intelligent manner. For example, if this frequency band at 1 second, for 1 second the communication system can use, and then the next second the radar system can use. So at the same time they are not using the same bandwidth, so it doesn't interfere. So this is one example how you can use the same bandwidth for communications as well as for sensing. And then when you use the same bandwidth, what happens is you must use the same transmit signal for both functionalities. So you have the same signal xt to do also communications as well as sensing. So like I showed you here, now there are two signals, signal xt and signal xct. But now when you have the same spectrum, then you should have just one signal, so signal xt. And this signal needs to be designed, or what we call optimized, considering both systems performance. So this signal needs to be designed so that you can have satisfactory data rate, let's say for the mobile users, as well as at the same time ensuring that what the sensing system measures is something reasonable with less error. And then when both of these things happen, then it also means that the same hardware can be used for both functionalities. So the same hardware system can be used for both communications as well as sensing. So it means that you use the same bandwidth for both communications and sensing. And then hardware convergence means you do that, but using the same hardware. An example is this kind of scenario. So this is what we will see coming in 6G. So now there is a base station or cell tower right? And then you in let's say in the first hour you use that only for communications, and then in the next hour you use that for sensing. So in that moment the communications is not happening in the second hour, but it is just like just to differentiate you the difference between, or even though they are using the same frequency bandwidth, they are not so happening simultaneously. That is just like
Time
but there are
based.
like, yeah, it could be time based, but that is just one example of when that happens. But it could also not be time based, and it could also be, they could be both simultaneously the same frequency and the same time as well. But then there is this interference, but then there are much research happening on how we can reduce that interference as well. So it could be time based, that is one possibility. But then the one drawback of this time base is that whenever the communication system is not transmitting, the radar system is transmitting. So they are doing during different times. But that also means for that when the radar system is transmitting, the communication systems or the mobile user phones, they do not receive anything. So that is also something that we don't want to happen. So what we want to have the same frequency, and we want to have being done at simultaneously, and then so that you can have both sensing functionality as well as communication functionality on the same times, and at the same frequency. But then there will be some more advanced concepts that you need to consider, how to reduce this interference and so on. But that is something that will probably happen so in the future. Was that clear? Yeah. Okay. Are there any more questions? Okay, seems not. And then let's move forward then. So yeah, so this is what the system that you will probably see in this integrated sensing and communication system. That means there will not be so much just radar systems, just communication systems, but now you have a combined system that does both. So yeah. And then some of the use cases for this ISAC or integrated sensing, which I show here. So one example is the automotive radar, like I showed, like I talked earlier. So you see, you have this kind of like a car, and then at the front there is another car. And suppose that because it's a self-driving car, it needs to be aware of its surroundings, like what are the objects or what are the obstacles in front of it, behind it, what are the cars next to it, and so on. So that is the function of a radar system. So the radar system will say, okay, there is one car at 30 degrees with going at a speed of this and at a distance of this. And then this information then would also need to be communicated with, let's say, there are these two self-driving cars, and then this information needs to be communicated to the front car, or the front car can see what is happening in the front, and then it can use this communicate this information to the car at the back. So it knows, okay, there are some obstacles here and there. So although I haven't seen that yet, I get that information from the car in front, so I can sort of adapt accordingly. So this is an example where you use both these communications as well as sensing functionality. And another example is this UAV. These UAVs nowadays, it's becoming more and more prominent. So there is a sort of a base station, and it needs to monitor, okay, there are two UAVs going, and so these two are here, this one is here, this one is here. So then it can, let's say, okay, coordinate the path. Okay, you need to go this direction because there is the other UAV here, and so and so. And so you see, from the sensing perspective, the base station or the cell tower will know where the different UAVs are. At the same time, then it says, okay, based after processing this information, it can tell to the UAVs, okay, you need to go this path, you need to go this path. So that is communication. So that is another example where you have this integrated sensing and communication functionality. And then another something is on digital health monitoring. So in hospitals, there have been even like nowadays, I've seen like many devices in this elder care facilities. So typically indoors you have Wi-Fi systems, right? And then there's the Wi-Fi router, and then there have been like so much progress in like how you can use this Wi-Fi system also to do sensing, and there are enough applications. So these are installed in this elder care facilities, and suppose that some old person falls down, and then it will detect this and then communicate this information to let's say like a central unit, let's say where the nurses are, and it will say, okay, in this room this person fell down, so just go quickly. So that is another example where you can see this integrated sensing and communication. And so there are this other example. So this is like downlink sensing. That is another important scenario to downlink. So in communications there is like two links, downlink and the uplink. So the downlink means the signal going from the base station to the user, and then here you have uplink. Uplink means the communication going from user to the base station. So down in the sense that it's coming from the base station to the mobile user, as up because it's going from the mobile user to the base station. So downlink sensing is another example. So you see now there is a base station, and it suppose that it first does the sensing functionality. So it knows where the different users are in the environment, and then it can only transmit communications data to only the directions that there are communications users. For example, consider on the left side there's like a very big forest, and there's on the right side that's where the city is. And then through sensing we can know, okay, on the left side there is a large forest, so we don't need to transmit anything, and then we can transmit the communications data only to the mobile users. But otherwise, without this sensing functionality, the base station would be, transmitting data also to the forest direction unnecessarily, and that is not useful for anyone. So that is another example where this ISAC would be important. And similarly, you can do the same thing in uplink, which means that the mobile phone is now doing the ISAC. So now it will communicate with the base station, and then the mobile phone will also see what are the the different objects in the environment. So for example, it would be beneficial in, let's say, like there's this some blind person or someone walking the streets, then it can know, okay, this is the road and these are the way. So it can give some indication if it's the blind person is moving towards the road. It can give some indication, no, you are moving to the road, just move to the left and just go through the road, something like that. So these are some examples where you see these use cases of ISAC happening. Okay, and then so then I talked about this ISAC, and then why this becomes why this is happening in 6G. And the reason, these are some of the key performance, like the key technologies that helps. So these ones, what I don't show here, these are the 6G functionalities that are useful for communications. So the first one is like dense network. That means in 6G, you will see base stations more closer to each other. So now, for example, in 5G, the base stations are not that, dense, but in 6G, you will see them more frequently. You will see them everywhere. So now you have a more and more dense network. When you have more and more base stations, that means that more and more you can transmit more and more data, because since the number of communication devices is so high, you need this more and more base stations. So that is one thing. And then the other thing is wide bandwidth. So like I mentioned, the bandwidth for this S-band radar I showed was this much compared to the Wi-Fi bandwidth. And now when you increase the bandwidth so much, that means it's obvious, like if there are more and more bandwidth, let's say in 6G, then Dialog, Etisalat, or these other mobile service providers, they can have enough bandwidth and they can have, transmit as much as they want. So when you have more and more wide bandwidth, that means it improves against the data rate and so on. And then this AI and signal processing. So now in 6G, there's also much research happening on how you can use this AI for improving the communications. So one example that was at Nokia Bell Labs is that traditionally in 5G, there are these traditional components inside the mobile phone's receiver, right? You have frequency filters, you have this different like advanced, let's say, like components. And then now we also have something called the deep receiver, which deep means it's a deep neural network, so instead of having all of these different components, you now just have like one deep neural network. So it receives something, and then it do this processing in the background, and it gives you more data rate than when compared to this traditional component. So that is some example where we use this AI in this processing. But anyway, so this is just also on the mobile phones user, but there are also this AI functionality on the base station as well, that is able to coordinate different services much faster than what you have nowadays. And then something called MIMO beamforming. So MIMO here, I denote that MIMO stands for multiple input, multiple output systems. So multiple inputs MI, multiple output MO. So that means this means that you have more and more antennas. Compared to earlier, where I used to have like one antenna, now we are having even like thousands of antennas in a very small area. So when you have this kind of like a MIMO systems, I will explain that later, the advantage. But yeah, I'll come back. So these are the main factors that helps for 6G, for communications, for improving the communications performance. But then talking about 6G, since we are also talking about sensing, the same features are also helpful in for sensing functionalities as well. So the first one is this high carrier frequency. So in 6G, you will see like carrier frequency is same as this center frequency that I mentioned to you earlier. So now you see some 6G systems will even operate beyond this. It's beyond the even like 70 gigahertz range. So now now the 5G systems is something is happening around, let's say 3.5 gigahertz, like 24 gigahertz. But in 6G, sometimes it's also possible to have it in like very high center frequencies or carrier frequencies. And then in those carrier frequencies, because there haven't been anything yet, any communication systems, you have much more wider bandwidth. So that's why when you go to more and more high carrier frequencies or center frequencies, you have more and more wide bandwidth. So that's the reason that we want to move to this high center frequencies. And then when you have wide bandwidth, that's good for communications because you have like more, you can accommodate more and more users and then more and more data rates, right? And then that is for communications, but for sensing, that does something called decrease in the range resolution, which I will talk a little bit later. So for the sensing system, the wide bandwidth helps in decreasing something called the range resolution, and that will be helpful for sensing systems. So I will get back to that later. And then, like I mentioned, multiple antenna systems, and it's good for communications, and then it is also good for sensing because it decreases something called the angle resolution, which I will also come back to later. And then the reason also why people want to more go for this RF signals or radio frequency signals is because it's good for privacy. I mean, you can do the same thing with cameras. I mean, you can have a camera system, so seeing, okay, what are the targets here and so. But then the problem with cameras systems is that you can identify the person. For some cases, let's say like military or other services, that's not so not good. So, but for RF signals, you cannot say, okay, if it's it's person A or it's person B, but it can say it's just a person. So that is another reason why this privacy purposes why these RF signals are useful. So yeah. So like I mentioned to you, I talked a bit about these multiple antenna systems or MIMO systems. So when you have a MIMO system, you have something called the beams. So as an example, consider that there are like K users 1, 2, 3, 4, up to K. And then if you have a multiple antenna system, you can transmit each user's data in a separate beam. So now what the user wants data, it's only transmitted towards user 1 and not towards user 2. So that is one advantage. So suppose that there are two people, and then in an earlier system, let's say 4G or some system, or even beyond, earlier if you want to transmit some signal, it will go to the person A as well as for person B. But person B doesn't want, for example, it could be a YouTube video. The person B doesn't want the person A's YouTube video. So then, because that is again, like I mentioned earlier, it is some kind of an interference. So if you can, so in this previous systems, you had to do some extra processing to remove this person, the other person's signal. So that took some power, and that was why it was one reason why it was reducing the speeds in those previous generations. But now when you have these multiple antenna systems, you can only send the person's A's YouTube towards person A and person B's YouTube video towards person B, something like that. So that's what I mentioned, that the beams can be focused at multiple users. And then on top of that, multiple users can have multiple data streams. So data streams mean that, for example, one person could be streaming YouTube, and at the same time it could be using Facebook, so and so. So then these are so each user can have different streams, data streams, and so with this one beam, you can send multiple users' data streams only towards that person. So that is the advantage of this multiple antenna system for communications. So the basic idea is that when you have multiple antenna systems, you can have separate beams focused at different people, and then each beam carries multiple number of data streams. So that is the advantage of a multi-antenna system, what I mentioned here. So that's why in 6G it is more useful, because you have more and more people nowadays using data, 6G services in the future. So then you should, I mean, if there are hundreds of people, you should still be able to, focus the users' data towards the different users. So that is why these multiple antenna systems are important. So all what I've talked here about these drivers for ISAC was in perspective of communications and not towards sensing. So next I will talk about what is meant by this range resolution and angle resolution and why that is being useful for sensing. So as an example, so range resolution, if I denote it short by delta R, it's the minimum range separation between two nearby targets which the radar can distinguish separately. So if it's a very long sentence, so consider that you have two objects, let's say separated by a distance d, and then this distance d is greater than this delta resolution, the range resolution or the delta R, then the radar system will see it as two separate targets. So suppose that if there are two cars separated by a 10-meter distance, and if the range resolution is 5 meters, so then the radar system sees, okay, there's one car here, one car here. But if the range resolution is less than the distance, the radar system will only see just a single vehicle, so something like that. So because for radar system, if it can detect more and more objects or vehicles in example, then it is much beneficial than seeing everything as just one target, right? So as an example here, I show consider that this is the angle domain from going from minus 60 degrees to plus 60 degrees, and this is the range, in meters, right? And then these are the different objects in the environment, and consider that there is a radar system at 0,0, and then you see here in minus 40 degrees, which I denote by theta c, 1, there are two objects, you see, at the same. So from the radar's perspective, they are on the same minus 40 degree angle, but there is a separation of around let's say 2.5 meters between this in range. So there is some distance, 2.5 meters distance in range, in distance, right? At the same time, consider these two targets. So you see these now have the separation is around 0.8 meters, but there is some angle separation of 2 degrees, right? And these are the other targets. So then this plot here, you don't need to focus so much on the different, like the legend, but what I've done here is I consider that, okay, there is some radar system here, and I transmit some signal, and based on the reflections, I'm trying to here estimate what are the ranges, what is the distance towards the different users or the targets from the radar perspective. So you see here in theta other, this direction. So you see here, although there are, one thing I forgot to say is that this is what is called like the range profile. So range profile means on the x-axis you have the meters, so that is the distance between the radar and the particular object or the target, and then on the y-axis it's basically how good, or like the power, or how good the reflection or the received reflections is. And when you have this like peaks, you see, that means there is a target compared to here where there is no target. So you see here in this theta, this direction, this OTH means other for short. And so you see, although there are two targets, you see 21.03, 21.80. So the radar system detects, okay, there seems to be some target at 21 meters, but it cannot separate it as there are two targets, right? But in comparison, if you consider this theta C1, so you see the radar system is now there are two peaks here. So the radar system is able to say, okay, there seems to be two targets at around 65 meters range. And so you see Now the problem in this theta other angle is that although there are two targets, the separation is around like, let's say 0.8 meters, but the range resolution of the system, which depends on certain other parameters, it is you see it is less, the distance is less than the range resolution. So suppose that if the range resolution is 1 meter, that means the radar system can only see targets with a separation of 1 meters. But because here separation is 0.8 meters, then it cannot see, because it will only see targets at a difference of 1 meter, but not at, because 0.8 is less than 1 meter, it cannot detect it. So it will show it as a single target. But here in theta c comma 1, so you see there are two targets, and the radar system was able to detect it as two targets, because now separation is 2.5 meters. And if the radar system, if the range resolution is, let's say, something like 1 meter, so it can correctly say, okay, there is these two targets, because the distance between the two targets is higher than the range resolution. So that is why this is actually what is meant by this range resolution. So like I mentioned to here, when you have more and more bandwidth, it decreases the range resolution. So from 1 meter, it can go to, if it goes to, let's say, 0.5 meters, then in this case, in theta other, there will also be two targets, but because the range resolution is now 1 meter, it cannot show. And the relation between, so here I mentioned, like, when you have wide bandwidth, it decreases the range resolution. So the reason is something like this. So in this, this is related to 5G, but so in 5G operated at two frequency ranges, something called FR1 and FR2. So FR1 was something less than 6 gigahertz. So the center frequency or the carrier frequency of this system was less than 6 gigahertz. But the problem with this less than 6 gigahertz was that the maximum bandwidth, so how wide along the center frequency, how wide the bandwidth is only 100 megahertz. But in FR2, which goes from 24 to 52, maximum bandwidth of 400 megahertz. So you see here on in this plot, the x-axis is the bandwidth, and then the y-axis is the range resolution. So you can see as you increase the range resolution, as you increase the channel bandwidth, you see the range resolution decreasing and decreasing. So you see here for 100 megahertz, that is the maximum bandwidth available in FR1. The range resolution is around, let's say, 2.5 meters, right? But then if you consider FR2, you could have even very low, I think it can go even until like 30 centimeters or something like that. So that means it is able to differentiate between two targets, two vehicles, let's say at even less, at separation of even 30 centimeters, something like that. So you see now why improving bandwidth is good for communications, because you can have more and more users, it improves your data rate, but at the same time, it decreases the range resolution of the radar system. That means the radar system can differentiate between targets with even like very, very, very small separation. So that is why this is important for sensing. So yeah, maybe it was too much information. Any questions on that? So did everyone understand the concept of range? Okay, yes, Tarak, go ahead.
Sahanda, that range resolution is not impact for the mobile. It's in mobile devices, right? Is that
No. Yeah, exactly.
Is it related only for radar systems, right?
Exactly. Yeah, because yeah, good question. So yeah, what I here wanted to say was that in 6G we will have wide bandwidths, and when you have a wide bandwidth, it's good for communications, because you can accommodate more users, you can put more data, and that improves your data speed. But then having the same bandwidth for the sensing system, what it means is it decreases this range resolution. So it is not related to communication system, because communication system, you don't necessarily talk about range resolution. It is not important. It is important for radar system or sensing systems. But now since we are talking about this integrated sensing and communication, the advantage of having a bandwidth, high bandwidth is it's good for communications and also for sensing. But if you combine integrate sensing and communications, then if we are able to say, okay, there are from the suppose there's a cell tower doing both of these functionalities, right? And then the sensing system first detects, okay, there seem to be two users separated by 50 centimeters. So they are very close to each other, but they have different, mobile phones, and they need to have different services. And then then the sensing system will tell to the base station, okay, there are two persons here. So you can use this information to improve your communications performance. So sensing system first tells you about the environment, and then the base station, it uses this information to improve the communications users performance. So as an example, it can say these users are now at let's say the sensing system can say, okay, they are at a separation of 50 centimeters at a separation of 2 degrees. And then this information, the sensing system can utilize in order to use these beams. It can then focus the beams more narrower without like when compared to without this information. So did that answer your question?
Yes, sir. Thank you.
Okay, yeah, thanks. Thank you, Tharaka. Any more questions? Remember, there are no stupid questions, so any question is fine. Okay, seems not, and then we can move ahead. So like I mentioned, this is something called the range resolution. So this is good for like I mentioned, the radar system typically estimates the speed, the range, and the angle, right? So having wide bandwidth is good to improve the range resolution. And then I mentioned here, having this multiple antenna system, it decreases something called the angle resolution. So it's the same concept as the range resolution, but it is just for the angular domain. So you see here, the angle resolution is the minimum angular separation between two nearby targets, which the radar can distinguish separately. So similar to this previous example, there are two targets in this, let's say, minus 30-degree angle, but because the angle resolution is high, then the separation between these targets in the angular domain, the radar system only sees a single target. But here you see the separation is higher than the angular resolution, so the radar system sees them as two separate targets. So then, like going back, so this would suppose that there are two users very close to each other with this angle, like this example I told you about the range resolution and the angle resolution. So ideally, what you want to have is very low angle resolution and very low range resolution. So if you have that, then the radar system can see very close, even very close by targets or objects or vehicles or people closer to each other, even with like a centimeter distance difference. And then the communication system utilize this information to improve the communications performance or the data rate of the different users. So that is what it means by the angle resolution. And angle resolution is delta theta is inversely proportional to the number of antennas. So that means if you have more and more and more antennas, it decreases the angle resolution. So in 6G, like I mentioned to you, you will have this very high number of antennas. So when that happens, you will have low and low angle resolution. So that is the advantage of having a multiple antenna system for sensing. So if I show here additional information, so the antenna size, maybe that's not so useful, but here, okay, maybe I can also, that will also some useful information. So the antenna size that you can make is proportional to the wavelength of the carrier or the center frequency. So I mentioned to you here, in 6G, we are going towards high carrier frequencies or high center frequencies. And when that happens, since it is antenna size is proportional to the wavelength of the carrier frequency. So you know this equation C equals F lambda, right? So C is the speed of light and F is the frequency and lambda is the wavelength. So that means since the speed of light is a constant, so that means C equals F lambda. F is inversely proportional to the wavelength, right? So So that means if you go more and more towards high carrier frequencies, that means it decreases the wavelength lambda of the different waves, and since the antenna size is proportional to the wavelength, what that means is that the antenna sizes also become quite smaller and smaller in 6G. So that means if you consider the same physical area and consider that 4G system having, let's say, like a carrier frequency of, I don't know, as an example, let's say a communication system having 10 gigahertz of center frequency, and now in 6G, if you have something like 80 gigahertz, that is an 8 times an increase of frequency. That means the wavelength is 8 times lower. That means the antenna size is also 8 times lower. That means for the physical area where there was one antenna in this first communication system with 10 gigahertz, for the same physical area, you can now pack 8 more antennas, right? So consider that this black one shows this first communication system. Let's say this represents one antenna element, but if you go to this more and more high carrier frequencies, then you can pack more and more antennas in the same physical area. So now in the horizontal axis, you can have MH, the H for horizontal, number of antenna elements compared to earlier. So similarly, it also happens along the vertical domain. So now if you have, let's say, the same physical area, you can pack more and more antennas. And like I mentioned to you, when you have more and more antennas, it decreases the because it's proportional to the number of antennas. So the angle resolution keeps decreasing as you have more and more antennas. So you see here, this is just one antenna, and you see this in purple, it's the beam that I introduced to you earlier, the beam that you transmit. So you see, with one antenna, you are transmitting everywhere. So this is something what you call this omnidirectional antenna. For example, in like Wi-Fi, you have something like this omnidirectional antenna because you want to send this information to everyone in the room. Okay, and then compared to see that when you have two antennas now, so in yellow you have these two antennas. So now you see there's something called the main lobe and the side lobe. So main lobe is something like the beam that I mentioned to you earlier. So now you see it has become more directional, more focused, and the side lobe, although side lobe is something that we don't want to have, so but we cannot control it. So you see, even though we want to transmit along this direction, there is some energy that is transmitted towards this side lobe direction. But compared to this one antenna element, you see now this other direction, unwanted other direction is much reduced. And you see now going from 2 antennas to 4 antennas, now the beams are becoming more and more focused, and the side lobes are also getting more and more smaller. So this is just with 4 antenna elements, but even in 5G, we have something like 64 antenna elements, and in 6G we will have something like thousands of antennas. So you can assume these main lobes will become like narrower and narrower with less side lobes. That means you can focus the beams very precisely at these different uses, and that is why this gives you improvement in the angular domain. And then also, since you can focus the beams towards the different users, it improves your communications performance. At the same time, it decreases the angular resolution. So it's also good for the radar system. Yeah. So again, this was also maybe too much information. Any questions on this? Okay, seems not. So I'll proceed. Okay. Now I'll talk about this joint signal design. So perhaps you forgot, but here now in this integrated sensing and communications, you have something called now I mentioned that you use the same signal XT for both purposes. So now there is the signal XT is a communication signal as well as a radar signal. And this signal, like I mentioned to you earlier, it needs to be designed or optimized considering both systems performance. So that is what I want to introduce to you here in the joint signal design. So now So this basically in 5G or in 6G, we have something, we transmit information like this. So we have something called time and frequency. So we call that the time frequency grid, right? That means, so suppose that the first column here, right, it shows the information that you transmit on the first time instant and what are the frequencies you transmit. So that is the first column. And the second one is you have a second column, you have the what you transmit the second and what information, and the third second what information, and this basically constitutes this resource grid. And then in this joint signal design, so like I mentioned to you here, it's basically considered to be an array. So an array or a matrix, it's a two-dimensional. On the x-axis you have time. So time means like at which instance you transmit. Frequency and means what frequencies you transmit. Like I mentioned to you, you have this bandwidth, and at one instance you can transmit a separate set of frequencies, and the next time you can transmit a second set of frequencies, right? So here now we are talking about this joint signal design, because now we have a single signal to do both communications and sensing. So here I denote this small box denotes the information that you send. So for example, each small box, this yellow box, for example, can be like a one frame of a YouTube video for sensing. But then sorry, it's the blue color. So the blue color ones correspond to the communications data, and then the yellow ones correspond to the in this case the empty one. So so consider that again. So I'll reiterate. So this is what we transmit from the base station. All right, there are these blue spaces which you transmit, and then typically what happens is in a communication system you don't have it all blue, meaning that there are empty spaces, and these empty spaces, what I've denoted them as as yellow. Okay, so the communications data, your YouTube video, your Facebook data are in these blue boxes, and then on top of that, the communication system doesn't necessarily always use all the resources, all the blue area, but it uses but there are some empty spaces, so these yellow spaces. And this what I do here is I fill these empty spaces, because these are not communication data, these are just empty spaces. I fill them with radar data. So that now the joint signal is now a combination of this yellow, which was empty, but which I fill with this radar data, I fill with some optimized or some I do it in some way, and then the blue data is your Facebook or the YouTube or this communications data. Okay, and then like I mentioned, I can fill these yellow spaces in some way, and I do it so as to minimize the errors of range and velocity. So as I mentioned to you here, if you check the table here, so the actual speed of a vehicle could be 40, but then of course a radar system cannot exactly always measure the speed, because there are some errors, there are noise, these different factors. So the idea is you should try to get the measured one should be more close towards the actual value. So if you consider there are two radar systems, and the first one says okay the speed is 37, the other one says speed is 20, you prefer the one with 37 because it's more close to the actual one. Similar to the range can be 100 meters, but then if there are two systems saying like 200 or like 150, 150 is maybe is too erroneous, but still you still prefer the 151, right? So what I do is when I fill these empty spaces, yellow spaces, I fill so that it minimizes the error, so that the radar system will be more close to the actual one. So that is how I fill these empty spaces. And then I have two questions. So there are this too much of yellow spaces. So I first have to pick where out of these yellow spaces, where to fill. So I have to select a portion of this, because I don't want to fill everything. I can, but for improving performance, I found this some like mathematical derivation. But anyway, I found that you don't need to fill every yellow space. There can be a set of space. So first I needed to find, okay, which yellow spaces I need to fill. And then once I decided where to fill, I wanted to fill it with I cannot just fill it with something. I had to fill it with something optimized. So that the second question was what to fill. So two questions, where to fill and what to fill. So I'll give you an example here. So consider this 2D grid to be let's say like when you go to a movie and there is like seats everywhere, right? And then the blue spaces are where there are people already sitting, and you see now there are many empty spaces that you can sit. So first, what you do it when you go to a movie theater, what you do is you will first select where the position, okay, depending on the screen and so and so. So then out of these every yellow spaces, every empty chair, you will select one or one chair. Let's say it's this one, right? And this is the first question, where to fill. And then what to fill is suppose that the same thing, but now a family of like let's say four people, four like mother, father, and two like son and daughter, they are going, and then the family will first decide, okay, where we will go. Okay, they will go probably to a central location, and then they will decide, okay, who sits here. For example, depending on the person, if it's someone with a like with it's tall, perhaps the father will go there, and if there's a children sitting in front, then the son would also be at the back. So the two questions are where to fill and what to fill. So I did this filling on these two questions, and then this mind you, this is just still a 5G signal I use. So 5G signal I use radar data. So I'm now using the same signal for both communications as well as for sensing. So I did this and then did this like practically, tried to do this with outside of the university. So this was the university. So here you see here in the transmitter and receiver. So these are something called horn antennas. So basically these are some antennas that are used for the transmitter and for the receiver. And then I generate the signal in here through MATLAB actually, and then did this some processing. This not important here, but then this transmit signal was as a center frequency of 28 gigahertz. So that is the important thing. So it was transmitted at a 28 gigahertz carrier frequency with a bandwidth of 400 megahertz. So if I go back here, so it is some so the signal that I transmit was somewhere around here at 28 gigahertz at bandwidth was around 400 megahertz. So yeah, and then I transmitted, and based on the reflections, I tried. So the signal transmitted was what I transmitted here. It was a 5G signal, and I filled these empty spaces with some things, and then the reflections, because in a sensing system or radar system, you transmit something, you get the reflections, and then you process them to see where the targets are. So this is what I did. And so I did not hear some important landmarks in the area. So this was the measurement setup. So you see here, I have this rectangle A, which is basically like a high tall building, and then this rectangle B, it's some sort of with grass and the wall, and rectangle C, it's like at the behind there are some vehicles. Sorry, there are some buildings. And then in rectangle D, it's the yellow one. There are, I don't know if you can see, there are these small like bicycles and some metallic structures for the trees. So these are the main ones that I used to measure. So what I did was I first transmitted this without filling. So that means I used the 5G signal with these blue spaces, but the yellow spaces, they were just empty. So that's the normal 5G signal without integrated sensing and communications. So I transmitted that and tried to estimate the map of the environment. And then the second one, there are empty spaces and I filled them with something. So that is the second step. So this is the two maps that I obtained in these two cases. So the first one, I did not have unoptimized. Unoptimized means that it was just a normal 5G signal with empty spaces, right? And then the optimized one, it means that I fill these empty spaces with some optimized data. And then on the y-axis, so then on this color bar, you hear the blue one. So these two maps shows like how powerful the reflections are. So if I go back here, it's similar to the range profile. So like I mentioned to you here, if you have more power being received from a certain direction or from a separate certain range, that means there is possibly a target. And then, so for example, here, there are two targets here at 20 meters, but nothing here because the received reflections power is quite low. So the same concept here, it's just that this is like now a 2D image. So now the power of the received signal is reflected here in this color bar. So you see have blue, which is less power. So probably that means there is no target there. And if you have more and more red, that means there is possibly a target there, and this shows the variation. So I here first will come back to the optimized one where I fill this thing. So now you see, I've denoted these ABCDs coming from this like different buildings and so on. So you see now here in D, you see there is this one bicycle here, one bicycle metallic structure here, one metallic structure here, and it's also sort of here. So it's sort of considered to be something like a 3x3 grid kind of a thing. So you see something like this here. You see here this red color here, red color here, red color here. These red colors, and then also yellow because because the reflections were not that strong coming from there. But in blue region, we can sure, because since I'm transmitting it from this this setup, so although I'm transmitting it towards this range, it is sometimes also possible for the signal to hit the ground, and then I also receive the ground reflections. But when you have metallic structures, so metal reflects energy much well, RF energy well, compared to just like normal grass or something like that. So when I receive this ground reflections, their power is very low compared to the reflections from the metal, right? So that is why this area is like, by the way, the color bar, it's in decibels. That means like 20 decibel difference means it's like 100 times more powerful, and 30,000, 10,000, and so on. So you see here the reflections in the red region, it's compared to the blue region, it's 10 to the power 6 times more powerful reflections you are getting. So you see now I've highlighted these targets here, A, B, C, D. So now you see D is more clearly, you can clearly see the D region, and also the C, because there is because it is a little bit far away. So when you have the targets far and far away, because the signal has to travel this much of a distance and then come back after the reflection, it reduces the reflection's power. So this shows, for example, A, it shows that there is some reflection coming from like around 40 dBs of power improvement compared to the 0. And then you see there is something here, something here, something here, and so on. And then this magenta color, this light blue colors, there are also some reflections coming from this, like, this structure and so on. So these are the targets that I observed from this environment. And then the unoptimized one, you see now, even though in this region, so in this region, there was the ground, but you now see, compared to this, if you can see, focus on these areas, this area is dark blue compared to the light blue here. So that means the power received in this region, for the unoptimized case is around, let's say, around here. So it's 100 times more than the reflections here, which means that although there are no targets, because these are just the ground reflections that are coming, ground reflections, these are not important to us. We are more focused on vehicles, like buildings, people, these kinds of stuff. So you see in the unoptimized one, so perhaps someone can say, okay, there seems to be some some target here, but in the actual case, it's not. It's just the ground reflections. So now you see, by using this unoptimized and the optimized versions, you are able to reduce the ground reflections, or we call them the side lobes. Like I mentioned to you earlier, the side lobes, there can be this unwanted energy. So to using this as this kind of like integrated sensing and signal, it decreases the side lobes, which means that the radar system will not say, okay, there is a target here, when there is actually no target. So that is something called like a false alarm. It's a false alarm because there is not actually any target there, but still the radar system can say, okay, there is some target there. So basically, I just wanted to here show the difference between this when I use just the 5G signal with empty spaces and the 5G signal with optimized, how you are able to see the targets more clearly with less false alarms and so on. Yeah, any questions on this? Did everyone understand, or was it not understandable at all?
Yes, Sahan. So to fill those gaps, what kind of frames you are using? Yes,
What kind of?
what kind of frames that you are using to fill those gaps?
What kind? Sorry, I couldn't hear.
What kind of frames, I mean, or what are the
Frames.
things that you? Yeah.
Okay, yeah. Okay, so like, as you know, in 5G, we are transmitting everything in. Are you familiar? Basically, we are transmitting like a complex symbols, like something with, let's say, 2 plus 3J, 3 minus 4J, something like this information. So every communication signal that you transmit is in every this kind of like a small block. It's a complex symbol that you transmit. So and then complex. So at first, what you want to transmit is some bits like zeros and ones, but then after some processing, you convert that into a complex number. So, and then a communication system can have its own complex number set, and then the radar system can have its own complex numbers. So, for example, in this, if there could be the difference between if I want to transmit 1 plus 1J compared to 2 plus 2J. So there's some kind of like optimization mechanism which I haven't showed you here, but there's some optimization mechanism happening that tells you, okay, put 1 plus 1J here and not 2 plus 2J, something like that. So it's just a complex symbol, it's a complex number that is being transmitted.
Okay, so the other thing is we are doing some research on, Wi-Fi tomography kind of things.
Okay, yeah.
So this is quite similar for that scenario, I think, right?
Exactly,
So,
yeah.
Yeah, so in that case, so as you explained, the Wi-Fi signals are omnidirectional, so it is transmitting for everywhere.
Yeah.
And so to pinpoint the objects, normally we use multiple Wi-Fi transmitters and receivers. So
Okay, yeah.
it is better if we can have kind of a grid-like structure. And if you have that grid-like structure, then we can actually pinpoint all the objects in the area. So
exactly, yeah.
We transmit the signals and maybe using RSSI or CSI, whatever the things that we received.
Yeah.
And based on that, we try to localize the object. So in this scenario, so I don't know whether I could not get the idea. So how you are going to pinpoint this, or how you are going to detect the devices? And the other thing is, so when we are using the 5G and 6G, so you say that the signal is become more directional, right? Then the range is, I think, getting smaller and smaller. So then again, how we are going to detect those devices in that particular situation?
Yeah, exactly. So in 6G, like you mentioned, the range becomes smaller and smaller because we are going into high carrier frequencies. They have something called like a high path loss. So that's why we need to densify. We need to have more and more base stations. So more and more base stations, I think it corresponds to what you mentioned as more and more Wi-Fi routers. So you have something like reference points through these Wi-Fi routers, and then it's similar to when you have more and more let's say more and more base stations, something like that. And then if I understood your question correctly, so if there is how do I pinpoint the targets? So basically that's where this actually, if I tell you a bit more about how I did it here. So because now I have
in this situation you have only one transmit and one receiver, right?
Yes, yeah. And let me elaborate it a bit more. So how I did obtain the maps was that I was first transmitting the signal at, let's say, 0 degrees, and then the receiver was also towards that 0 degrees. So I was receiving reflections from that. So I transmit something at 0 degrees and I receive something at 0 degrees. And then I rotated the transmitter. Because these are horn antennas.
Right. Now it's clear. So that's
Okay.
why I was thinking. So you are actually rotating the
exactly.
Right.
Yeah, good question, because I couldn't mention that about the rotating, that how I was. But in the Wi-Fi case, since it's omnidirectional, I suppose you are receiving reflections from all the directions.
Yes.
And then
we are collecting things actually reflected from the other surfaces as well. Right?
Exactly. Yeah. So I think that in a sensing system, that is I don't know if you're using this is something called like a monostatic system and a bistatic system. Monostatic system means that the transmitter and receiver are co-located. So it's something like a 5G base, but in bistatic, transmitter and receiver are separate distance. So this is actually a monostatic system, even though they are transmitter and receiver. There's like very few centimeters of difference, but I think in what you explained was something called like the bistatic system, if I understand correctly. So you transmit from some place and then you receive from some place, right? And then you process the transmitter receive signals to get the map of the environment.
Yeah, kind of. Yes, kind of. Yeah.
Okay. Yeah. I don't know if it might also be possible to use the same Wi-Fi router to do the receiving, but then
we have done something like that as well. So both the experiments were done. Yeah.
Okay, yeah. So the one issue with this, when you have the transmitter and receiver in a monostatic system, that means if you use the same thing for transmit and receive, the problem is when you are transmitting and if you are at the same time also receiving, so the transmit signal can also leak to your receiver. So because the reflections you receive, they are much weak, right? They reflect. So you are receiving the reflections very weak, but then the transmit signal, since the transmitter receiver are very close to each other, what you receive, you sometimes might not receive any reflections because the transmit power is the leak power. Yeah, exactly. The leak power is so much. So there is some research done that is actually called self-interference. So like I mentioned to you, this is self-interference because you are the person interfering on yourself. So there are some these self-interference cancellation methods where you can sort of remove the leaked signal and only receive the reflections. So yeah.
Yeah, thank you. The other one is so I'm not familiar with 6G. So so we are increasing the carrier frequency, right? So we go up to a higher level of carrier frequencies. So what about the power consumption of these things? So I mean, you are working in this 6G area. So we are talking about the wireless devices, mobile devices, and working with higher frequencies. So how that affect for the power consumption of the devices?
Yeah, that is a one research area. Like your question is one research area that is being researched in 6G, because like I mentioned, this sustainability, it's also like becoming more and more important, because if you have more and more base stations, that means of course you need more and more power, you need more and more electricity. So in 6G, it is also being done at like, let's say like an energy efficient manner. I mean, if I mention to you in like a numerical number, I think in the transmitters there are some limits that you can transmit. You can in 5G you can transmit between this and this range, but not more than that, because it can sometimes harm the environment and so on. For example, if I remember correctly, it was for 5G the maximum was around 43 dBms. So not decibels but dBms. So that was the transmit power in that case, but it can vary between different scenarios. So also like you mentioned, like the power consumption is an important like question, like how you can reduce the energy, that means how you can reduce the power but also give the same performance, same data rate and something like that. So an example is that in 6G there will be something called like like switching off the cell when there is less load, which was not in previous systems. Or then there are something called like muting, where you only you have, let's say, like thousands of antennas, but you mute. That means you don't transmit from these antennas, but you mute certain antennas, and then you do not transmit from those, and so and so. So basically, yeah.
Yeah. Yes. Thank you, Sam.
Yeah.
So
Thanks,
in a 6G situation, so if you have a base station, so the signals are more directional. That means you have to have a set of set of antenna arrays covering the entire area, right? So is that
Yeah.
the normal architecture?
Yeah, exactly.
Okay.
So that is what is this is MIMO meant, multiple input, multiple output.
Okay.
That means, I mean, nowadays in the mobile phones, maybe it's like 4 antennas, because you cannot put so many antennas in the mobile phone. But so
Yes.
then you are trying to increase it in the base stations, because 5G it's now just MIMO. It's just like 64, 128 antenna panels. But now in the future 6G, we have something called massive MIMO. So it's like thousands of antennas because of this going into high carrier frequencies and so on.
Okay. Yeah. Thanks.
Yeah. Okay, and then I think, yeah, I'm just like last 2 slides. So like I mentioned, these multi-antenna systems. So so the advantage of the multi-antenna system is you can have these narrow beams, right? So you see here a scenario where there are 4 users, communication users, and there are 3 targets. So because when you have a multi-antenna systems, you can have separate beams. So so what I showed you here, like what Tarendu asked, was this is like a horn antenna, but I was rotating them mechanically through some kind of like a motor mechanism. But then it will not be the case in 5G or 6G. These are something called electrical scanning. That means you sort of you do not do them like in mechanical manner, but rather do them electrically. There are like certain ways how we can do it. But anyway, through doing that, you are able to then transmit the radar beams towards the radar targets, whereas you can also use the communication users. We can transmit the communication users data towards that direction. So this is the advantage of this multi-antenna MIMO systems, where you can transmit separate data streams through separate beams to separate users, whether it be communication or whether it is sensing. So as an example, is like a similar example that I mentioned here. There is like a ISAC system here at 0,0, and these are the targets of the environment, right? And then in this live blue dot and then this yellow covering, these are the communications users, and then the stars, consider them to be the radar targets, right? And then what I did here is I can so there are 3 cases here: sensing only, communications only, and ISAC. So sensing only means that I change this sort of electrical beam patterns so that I only have the sensing beams and not the communication beams. So as an example, that means that I'm transmitting energy only towards this beams, towards this, because it's sensing only. I'm only transmitting them towards the stars, these purple stars directions, right? So I'm not transmitting energy towards the communications users. So and this x-axis, sorry, the first row, if you see the axis, it's the range versus angle. So the angle is the y-axis and the x-axis is the range. And then on top of that, I consider these targets are also moving. So instead of static, they are also moving targets. So on the x-axis, you have meters, and on the y-axis, you have the velocity, right? So if you have the sensing only beams, right? So that means from 0,0, you only transmit beam towards these 2 directions. You see, these purple ones, since these are the radar targets, you see in the map, in the range angle map, you see the targets clearly. These are these yellow targets that you are able to see, but the communications ones you don't see, because you don't transmit much energy towards that, but there can be some leaking of energy, but you cannot see so much the target. And then if you observe the range velocity map, so the purple ones here correspond to C, so you clearly see the radar targets, but you also tend to see something from the the yellow ones correspond to the communications users. So you see, even though we are not transmitting energy towards we are only transmitting energy towards the stars, since there can of course be some energy being leaked to the communication users, you tend to also receive them, and that's why we are able to see this, right? This is the sensing only case. And then communications only case is when I don't transmit energy towards the stars, but only towards the communications users, right? And then you see now at here, you don't see anything because I didn't transmit any energy there, but I tend to see that you see here, there are some yellow stuff happening. So that those correspond to the communications users. And similarly, on the range velocity map, you can see now these are the radar targets range and the range velocity map. They are not observable here because I wasn't transmit anything there, right? But then I'm now only seeing the communications users, like the ranges, like where the communications users are and so on. And then ISAC, which is basically you have both communications and sensing. So I here denote the corresponding maps. And in this case, you are able to see both the radar targets as well as the communication users. So that's just what I wanted to say here, that in an ISAC system, you can change the beams through this because we have multiple antenna systems. And when you only focus them towards the sense, you can either focus them on, you can have the beams only towards the radar beam. So there is no yellow in that case here in this figure. And in the second case, there can be only yellow and no blue. But more ISAC case is when you have both blue and yellow, and then in doing so, you will be able to see both the radar targets, for example, vehicles, as well as the mobile phone users through having this multiple antenna systems. Yeah, and then as a conclusion, ISAC would be integrated sensing and communications would be a key technology in 6G, and then RF and hardware convergence, this same bandwidth, and then because of that, the same hardware resulted in the development of ISAC. And then high bandwidth and MIMO systems would be important for communications in 6G because it gives more data rates and it able to give you like narrow beams. At the same time, you can improve your resolutions in range and angle. And in talking about this ISAC system, you will be having a joint signal XT that I mentioned to you earlier, and it needs to be used to improve the ISAC performance. So you need to optimize in some way. You cannot just combine these signals together for ISAC, but you should combine them and optimize them to improve the ISAC performance. So that's all I have to say today. Thank you very much for listening and your questions, and then I'm also open for more questions if you have related to this one or any other question. If I don't know if I'm able to help. And by the way, also a special thanks to Tarindu for inviting me. Thank you very much, Tarindu, for the